would be running over the volume of space that you're considering. So there is an element of volume, maybe a D3 R, and you would be integrating the cross product of R, the position that you are considering when given in the integration, times the cross product with rho. So rho is a function of position. Yeah, so that's the mass density at the location R, multiplied by the speed of the flow at the position R. Right. So you could also you could think of rho multiplying the D3R, so that would be a little element of mass, and you add up all the angular momentum contribution from these elements of mass, right? So this is for angular momentum. And maybe you remember in your electromagnetic class that you went through a calculation that started by considering the vector potential and expanding. Can you hear me? There were incredible sounds on my end. Can you hear me?
Yeah, I can hear you now. Yes.
Yeah, there it was. We heard it though.
At some point in your electromagnetic class, you have considered multiple expansion of the vector potential, and that led you to write the expression for the magnetic moment. And so what you found, we're not going to go through the derivation, but the result that you obtained when you did that was the following. You wrote the magnetic moment, it's a vector, and you wrote, there is a factor 1/2 that comes up, but you wrote an integral over volume as well. So we have a D3R times R cross product with J of R, where J is the electric current density, right? The J of R, you also wrote this, J of R. You wrote it as rho, maybe I'm going to call this rho sub Q to indicate that it is the density of electric charge of R times V of R. The speed at which the charges are moving at the location R. And so you see that these two expressions are analogous to each other. The only difference between them is that in one case you're dealing with a mass density as a function of position, while in the other case you're dealing with an electric charge density as a function of position. That's the only. Let's back to the notes. I just wanted to remind you of this. So let me go back to sharing the screen. Okay. And so you have this relation. So you see you have a simple ratio. So you see that the ratio between the magnetic and the momentum is the ratio between the charge, the total charge, and the mass in the case of a point-like particle moving in a circular motion, divided by 2. So the 1/2 here is coming from the 1/2 that I mentioned. And the ratio between the charge and the mass is just coming from the fact that we have seen that in the magnetic moment, the difference is that in one case we consider the mass density, in the other case we consider the charge density. So that if you had an object that is spinning, you could describe this spinning object as a collection of points like this one, following a circular orbit at a constant rate, and the ratio between the angular momentum of this object spinning and the magnetic moment that is resulting from that from the fact that this object is charged and spinning. That ratio would just be that ratio that I wrote here. Now, in fact, the distribution of mass and the distribution of charge do not have to be the same. And so we introduce this G factor. So we're going to write that mu, the magnetic moment, is equal to the angular momentum, which I wrote S by reference to spin here, because that's the intrinsic angular momentum of the object that we're considering. So we still have this Q over 2m that's coming from the orbital motion description that we went through before. And we add this factor G. And this factor G is the gyromagnetic, I don't know if I wrote that here, I don't think I did. That's the gyromagnetic factor or ratio, gyromagnetic ratio. And in the case of the electron, the value of G is equal to 2. That's not exactly true. It is equal to 2. It would be equal to 2 strictly if so if the electromagnetic field was not associated with any interaction, it would just be 2. And that number 2 comes out from a relativistic description of the electron, which we're not going to cover. That's something that is known as the Dirac equation, which was published, I think, in 1928, around, or 29, I forgot. And that's really something that comes from the mathematics of it. Now, in fact, an electron, so first of all, you would not talk about electromagnetic fields if they were not useful for describing interactions, right? The fact that there are interactions surrounding the electron changes that, that value G equals 2 by a small amount, which can be calculated or predicted using the quantum field theory that describes electromagnetic radiation. But that's something in which we're not getting. Saying that what is behind this factor of 2G for the electron is quite interesting. That involves relativistic quantum mechanics, and that involves quantum field theory that is used for describing the interaction property, electromagnetic interaction, as quantum electrodynamics. That's the name of the theory that describes electromagnetic interactions. Other particles, like for example, the proton, have a gyromagnetic ratio that is different from 2. These, we're going to see that the electron has a spin, so an angular momentum of 1/2 times h bar. And the proton as well, and so the neutron, but you see that they have different gyromagnetic ratios. And that has to do with the fact that the protons and neutrons, they're all made of quarks. So they have the quarks of, each quark is a spin 1/2 particle. Each proton or each neutron is made of 3 quarks. And the spin of these quarks, they combine together in some ways, but the magnetic moment that results from the combination of all these particles together exceeds the magnetic moment that is due to a single electron. So we end up with a in the case of the neutron, this, but just to say that there is a lot behind this factor when describing particles. In the case of the electron, G equals 2, that's a calculation that you can do on paper relatively easily. In the case of nucleons, like protons and neutrons, that's all. And theoretical work is done to estimate these quantities is highly intensive computationally, and it's very hard, very difficult business. Okay, and here I comment on the Dirac equation and the fact that the value of G is not exactly 2, but it's more than 2 because of some corrections having to do with electromagnetic field. So with this, we can turn to any question about this. Maybe I should pause and ask if you have questions. Any question?
No, everything's pretty clear up till now.
Okay. Now moving on to Stern and Gerlach experiment. So the idea is the following: they take heating oven essentially, in which they had silver, and since silver was heated to a sufficiently high temperature, some atoms were kicked through some collimating slits, just to select atoms that are flying in a very well-defined direction. And these atoms, they were sent in a gap between the jaws of a magnet, with a north pole at the bottom in my drawing and the south pole at the top in my drawing. The north pole was kind of shaped with a point in such a way that the magnetic field at the bottom of the gap is quite greater than at the top. So because of, so you have a magnetic, so the atoms, they have a magnetic moment. In the case of silver, the angular momentum of an individual atom corresponds to 1/2 of h bar being the Planck constant divided by 2 pi. And associated with this angular momentum, there is a magnetic moment. The magnetic moment is set by the spin, the angular momentum of the atom, multiplied by some gyromagnetic ratio, which I don't even know exactly what it is in the case of, or it must be the gyromagnetic ratio of 1 electron. And you have, when you have a magnetic moment inside a magnetic field, you have two things that happen. One thing is that there is a torque that is exerted on the particle as a result of the interaction with the magnetic field. And this torque, I wrote that here actually. The torque is equal to the cross product between magnetic moment and the magnetic field. And maybe you remember, or I hope you remember from your study of mechanics, that the torque is the rate of change of the angular momentum, which means, I don't, you cannot see me here. Stop sharing. That means that if you have a magnetic field that is pointing up, and you have a magnetic moment that is pointing at some angle with respect to this magnetic field, you see that the cross product between vectors along my two fingers here would be pointing maybe toward you. So that means that this magnetic moment, or the angular momentum that is associated with it, would be changing in this direction, right? So as a result of this cross-product interaction, the magnetic moment is going to be precessing this way. That's called Larmor precession. That's maybe something that you have studied before. And that Larmor precession, in the case of silver atom, let me share the screen again, is very fast. Oops. Okay. It's very fast. And so the fact that there is a horizontal component of the magnetic moment that is oscillating fast, that just average out as if it was not there anymore. And the only thing that matters is that there is there's a vertical component along the z-axis, if you will, in this figure, that remains constant in the course of this precession. Now, the other thing that happens is that the magnetic moment has a potential energy in the magnetic field, and this potential is obtained by calculating the dot product between the magnetic moment and the magnetic field with a minus sign. Okay? So that means that if the magnetic field and the magnetic moment point in the same direction, the potential energy is lower than if the magnetic moment points in a direction opposite to the magnetic field. Okay? And since there is a potential energy associated with the interaction between the magnetic moment and the magnetic field, there is also a force that is acting. So there's a torque, which we discussed already, which does not really affect the result of this Stern and Gerlach experiment. But there is a force that you would calculate as the gradient of minus the potential energy. But since the potential energy is minus mu dot B, then the force is just gradient of mu dot B. Okay, and so of course the value of the magnetic moment does not depend on position, but since the magnetic field in the gap is not uniform, there is a dependence on position here. So if you look at the Z component of this force, you're going to find that it's equal to mu dot product with the derivative of the magnetic field with respect to the Z coordinate. And if you concentrate on the vertical component of the magnetic field, you obtain just the Z component of the magnetic moment multiplied by the derivative of the Z component of the magnetic field with respect to the Z coordinate. So that means that these Z components of the magnetic moment and magnetic field are responsible for the component of the force along the vertical direction, which means that depending on the configuration of the magnetic moment in this magnetic field and the variation of this magnetic field, the particle is going to drift upward or downward. Okay. Here we have the derivative of the Z component of the magnetic field with respect to the Z coordinate that is negative, right? That corresponds to the fact that as you move up, the intensity of the magnetic field decreases. So that means that when the Z component of the magnetic moment is positive, the particle is going to be deflected downward, while when the Z component of the magnetic field, the magnetic moment is negative, the particle is going to drift upward. Any question about this? Someone confirm that you're still with me.
Yeah, I have a quick question. Could you repeat how we determine which is the Z component, Z direction?
Yeah, maybe I should have indicated on my drawing here. I'm thinking of the Z-axis being pointing vertically upward. And so in general, the potential energy is mu dot B with a minus sign. Then I take the gradient of that potential, grade that potential energy. And then I just concentrate on the Z component because I'm interested in the vertical displacement of the particle as a result of this magnetic field. And so I concentrate on the Z component, which I do here. But you see that mu, the magnetic moment, does not depend on the position, right? So I'm just left with the Z component of the magnetic moment multiplied by the Z derivative of the Z component of the magnetic field. And depending on that component being of the force being positive or negative, the particle is going to drift upward or downward. You're good?
Yes, thanks.
That's good. So now you have to place yourself in the mind of Stern or Gerlach. I let you choose. In 1902, you have to realize that as well in 1905, Einstein published one of the three important articles that he published was about Brownian motion. Brownian motion is the fact that when you look through a fluid with a microscope and you look at the particle, the first time it was observed was by observing pollen that was in suspension in water. You can see the particle that moves around, that drifts to have erratic motion. That is understood nowadays as being a consequence of the fact that the fluid is made of discrete atoms are colliding with that small particle that you are observing. And so he wrote a paper on that topic, and that paper was then used by physicist Perrin, Jean Perrin, to calculate the Avogadro number. And that was also a proof of the existence of atoms. But there were people skeptical, right? And so, and this was just 15 years before, right? So it's not a very large amount of time. So that means that at the time when Stern and Gerlach did the experiment, people were still, some few weird people maybe, were still doubting the existence of atoms. That was an idea that was still there, right? But so if you believe that there are atoms, which I encourage you to do, you would imagine these atoms shooting from the oven with, if they carry some angular momentum, that angular momentum pointing in one direction more than another, right? So you would expect the atoms to be successive atoms emitted by the oven pointing in random directions. And then depending on the Z component of the angular momentum of one given atom, and therefore depending on the Z component of the magnetic moment of that given atom, that atom is going to drift upward or downward by an amount that is set exactly by the component, the Z component of the magnetic moment. So if the magnetic moment has a magnitude of mu, indicated here, then you would multiply that magnitude by cosine theta, where theta would be the angle between the direction of the magnetic moment and the z-axis, and that would give you the mu z, which we wrote here, and that which decides by how much the atom is going to be drifting up or down. Up or down just depends on the sign, and by how much just depends on the cosine theta that is here. And you have a postcard that shows what they observed. So they were shooting atoms through a slit. The picture was recorded without the presence of a magnetic, so you have a clean kind of a negative shadow of the slit. Only reaching the screen that was sensitive. It was a photographic film, in fact, that is sensitive to ionizing particles. And so where the atoms arrived on the field, there was a dark line that appeared when the film was processed. And then they turned on the magnetic field. And for those that were going right in the center of the magnet, if you go back here, that's where the center of the magnet, that's where the gradient of the magnetic field is going to be the largest. That's where you have largest deflection, and you see that there are some particles, some atoms that are deflected, let's say up, if up is left here, and down is on this picture. No. So suddenly, while you were expecting, like classically, you were expecting a continuous deflection between some largest value down to some largest value up in the deflection. Instead, there was a discrete choice between being deflected up or down by a set amount. So it's something very, very certainly at the time and not expected. So that clearly is a first manifestation of a phenomenon. And I'm going to use, and I don't want to discussing how practical the experiment would be. In some cases, the conclusions that I'm going to draw, they were not drawn from exactly that specific experiment using a Stern and Gerlach apparatus, so a system of magnets between which you shoot atoms like that. And so in some cases, the conclusions that we are reaching were obtained from different types of experiment. So let's go. So a first experiment, if you had the Stern and Gerlach apparatus, the first experiment that you would like to do probably is to receive atoms from the Stern and Gerlach. So I call it Stern and Gerlach apparatus sub Z when the magnetic field is pointing along the Z-axis, okay? So let's say upward in the lab. And so we would have atoms arriving, their magnetic moment presumably is oriented in a random direction. And some atoms will be found. That's the Stern and Gerlach result that is illustrated in this picture here. Some atoms are found with angular momentum pointing down. Some atoms are found with a angular momentum pointing up. And what we could do is, for example, block those atoms that are found to have a magnetic angular momentum pointing down. Those atoms that are not pointing up, we would send them through a second Stern and Gerlach apparatus, which which would also be measuring the Z component, so which would be deflecting up those particle angular momentum pointing up and down those particles with magnetic momentum pointing down. And if you were to do that, what you would observe is particle reaching the second Stern and Gerlach apparatus with the angular momentum pointing up. And I'm sure probably you're thinking, well, that's what you expect, because all the particles were found with an angular momentum pointing, you kept only the particles with an angular momentum pointing up, and you're going to only find particles with angular momentum pointing up. This seems quite expected. Then, you make a second experiment, which the first part is the same. You have a stellar experiment whose axis is pointing along the Z direction. And then you make another, you set up another Stern and Gerlach device. This time the magnetic field is pointing along the x-axis. So for example, here, this could be the first Stern and Gerlach apparatus. And we would block maybe this beam, and we would send to Stern and Gerlach apparatus with the magnetic field pointing into the page, for example. Okay. And what you would see is suddenly you have so you're selecting particles with the angular momentum pointing up along the Z-axis, and then you move along the X-axis and you find as many particles pointing to the left or pointing to the right, the angular momentum along the axis. And so it's still surprising that we just have these discrete values of the angular momentum, either plus or minus some constant over 2. But it kind of seems natural that once you have selected, let's say you have fixed the Z component of the momentum, well, this component, in full, you don't know anything about it. So it's not too surprising that you have two different values, that there are as many particles with each of the two values. What is surprising is this quantization, discretization of the outcome of the measurement of the angular. Then maybe do another experiment where this time you would combine 3 Stern and Gerlach devices. So the first one would be the same one as in the 2 previous experiments. Then the second one would be the same as the previous experiment, so measuring the X component of angular momentum. But this time we would block, let's say, the particles that were found with an X component of the angular momentum that is negative, for example. And those particles that make it through a positive component of momentum, send them through a Stern and Gerlach device that measures the Z component of the angular momentum. And that is surprising, because what you observe if you do that is that you would have as many particles found with an angular component of the angular momentum pointing down, or with a negative component and positive components. And this is surprising because you started from a group of particles that you have selected purely composed of particles whose angular momentum was pointing up. Then you measure the x component, which classically should have nothing to do with the z component. And if you measure the z component of these particles for which you have measured the x component, then suddenly you recover the same number of particles, that's not the same number maybe, but the same fraction of particles with their angular momentum pointing down. Well, you have removed here. Before moving on, let me give an example with which maybe you are familiar even experimentally. And I'm thinking about optical polarizer. You know that light being a transverse wave, it can be polarized, linearly polarized. So you could think of the Stern-Gerlach device being replaced by a polarizing filter. And the polarizing filter by itself blocks the light that is, let's say the axis of the polarizer is vertical. So the vertically polarized light is going to go through, while the horizontally polarized light is not going to go through. And then if you run through a different polarizer, let's say, same polarizer pointing along the z-axis, then the light that went through the first one is going to go through the second one as well. If, however, light is different in the sense that if you were to have a polarizer, a first polarizer along the z direction, and then a polarizer along the x direction, how much light would go through the second polarizer? You are with me?
None, right?
Yeah, I
None.
can hear you.
If you cross two polarizers, no light goes through, right? Now there is an experiment you can do. If you have 3 pairs of polarizing sunglasses, or if you have 2 pairs and you break them, so you have 3 polarizing filters, you could set a first polarizer along the vertical direction, along Z. Then a second polarizer, maybe not along X, but with Z, let's say 45 degree. And then along Z again, and you would have light through, right? So it's a similar situation. In fact, what you could, let me share the screen, the camera again. I don't know if you have done that experiment. You understand what's going on, but it's still surprising. And it doesn't look quantum at all. It looks classical. Let's say you have light that is propagating along this axis, X. And maybe I have a first polarizer that selects light that is polarized vertically. Okay. Then here I have another polarizer that selects light that is polarized in the plane of the blackboard. I don't know if you see the attempt at a perspective drawing that I'm making. So you have light that arrives here. Let's say half of the light, assuming the light is not initially not polarized. Half of the light goes through the polarizer, right? And going through the second polarizer, there is no light that goes through because you have selected the light that is polarized vertically, so there is no light polarized horizontally that is left. Right? But let's say now that in between, you add a, so this is the x-axis, parallel to this one, z-axis, let's say, let me call it y-axis, I don't know. And instead of putting a polarizer along y or along z, I'm going to put a polarizer at, let's say, halfway between, at 45 degrees. And then by adding this polarizer, suddenly I'm going to allow light to go through the second filter. The reason for that is the first polarizer selects the light that is polarized vertically, but the vertical has a component along the second polarizer that is at 45 degrees from vertical. So then all the light that goes through the second polarizer is going at 45 degrees from horizontal. And therefore, there is a component that's going to go through the third polarizer. Right? But if I remove this polarizer, the light is blocked. So by adding an obstacle, I increase the amount of light that is transmitted. Has anyone played with that?
Yeah, I think it's, if I recall correctly, I think it was an experiment in one of the undergraduate labs. We have to do.
I don't. That's possible. That's possible. But it's amusing because it goes against your intuition. When you add something, you expect that it's going to block more, while in fact it does the opposite. Right? So it's amusing. And what's happening is that, I mean, the way you understand what's going on is that you make a first measurement of the polarization. And the question you're asking is the light polarizing? Is the light polarized up, or is the light polarized horizontally? Right? When you just have light that is polarized up vertically, that is selected, then you make a second measurement of the polarization at 45 degree angle from the first one. And the fact that you operate this measurement on the light changes the state of the light. The fact that you measure the polarization at a 45 degree angle changes, so the state of the light that is here after the second filter is not polarized vertically anymore, right? So that's how you understood that experiment, by saying, okay, the second measurement of the polarization changed the state of the light that was selected by the first measurement. And of course, that changes, since the state is not the same, it changes the outcome of the third measurement. So the situation is very similar. So the physics is different because in one case we're talking about light, while in the other case we're talking about electrons, and there is something funny about electrons that explains that difference that we'll discuss at some point. How do I go back to sharing here? I'm taking more time than I meant. Anyway, so that's you don't understand that experiment. The fact that there is a measurement of the x component of the angular momentum is changing the state of the electrons that were selected by the first measurement. As a consequence, it affects the outcome of the measurement that is done by the third device. Okay, and then there is maybe a third or fourth experiment. Imagine now that you have a quick succession of Stern and Gerlach apparatus. You see that there is a short one with South Pole up, North Pole down, followed by a wide one that is South Pole down, North Pole up. So that means that the first one is going to separate the beam of atoms in two beams. And one beam will correspond having a positive component of the angular momentum along the z-axis, while the other one will have a negative component of the angular momentum along the z-axis. But wider magnet with reverse direction for the magnetic field is going to recombine the two beams together. Of course, if you did nothing after this one, the two beams, they would cross, right? And so you want to add one more magnet that just brings the two beams together again. Okay, so that means that you come up with angular particles with an angular momentum in the state that you have prepared, and we're going to use that next. Then you separate them in two different beams according to the z component of the angular momentum, and then these two beams you recombine them. So if you have such a device, and you were to feed the input of this device with particles that have been selected for having a positive component of the z positive value of the z component of their angular momentum, and you were to send the output to a second Stern and Gerlach device that also measures the z component, then you would observe that all the particles are along the Z component, with a positive component of their positive value of the Z component of their angular momentum. If, however, you were to, so that's it. Essentially, the fact that you have physically separated those two components. So here it was a line along X, I'm sorry. So this device was selecting whether the component along X was positive or negative. So you separate the beam of particles that have been selected for having their Z component of the angular momentum to be positive. Then you separate them into two beams depending on the value of the X component of their angular momentum. Then you recombine them, and then you cannot tell anything. Then, of course, if you were to add some obstacle on one of these lines, on one of these beams, so that they don't go anymore, then right away you would see as many of the two possible signs for the Z component of the angular momentum. And the only way to understand that, so you see you have particles that are in one state, and they are separated depending on something that looks like a different state, but then and you get the same thing that you had at the beginning. The only way to describe that is maybe something that you have seen if you have studied a little bit of optics, that's interference. The result that is measured on combining some sort of superposition principle particles that have two different histories. And since all the experiments that we have described, you can do them with a very large number of particles flowing all very high rate. You can also do them with those going one at a time. So if you could think that every second you send one particle here that is selected for its Z component being positive. That particle classically would either go up or down in the beam splitter here, but the two history we get recombined by the last set of magnets, and the state would be the same again. While if you block one of the two beams, then you would have the two possible outcomes of Grassmann that would come up with the same probabilities. So since it works with individual particles, we have to talk about probabilities. Since there is a mechanism that can be understood only in terms of amplitude of interferences, we're going to talk about probability amplitudes, and the probabilities resulting from these probability amplitudes, they will be calculated as the magnitude square of these amplitudes. So we're going to stop here for the material today. Are there any questions? And I was much longer than I was anticipating. I apologize. Any questions?
Are you going to be posting these lecture notes on Canvas too?
Yes. Okay. Let me close. Shit. I don't know what I have done. Let me close that tab. Let me go to, so, okay, let me go through that again. This is the home page, right? And if you go to the class outline, you have some sort of calendar. And you see that under today's date, you have a link to these notes. So they are there already. And in fact, I sent announcement or something like that on Canvas, suggesting that you have a look at these notes. And clearly, it's going to be more efficient if you do that, because then you will arrive to class with maybe a question in your mind already. So please try to have a look at these notes ahead of time. You know, I'm not asking that you study them in detail, but sufficiently to have some understanding or some perception of your difficulties at understanding material, okay? And so you see that for next time, for example, you read the notes that are in this link here. Oh, I'm not sharing my screen. No, you are seeing my my screen, right?
Yeah, I
Yeah.
got it. Yeah,
Yeah.
thanks.
That makes sense. So any question? Any question? Once?
So I have a question. I think you kind of talked about this already, but I didn't quite understand. In this, like, I guess it's like a 3-layer Stern-Gerlach experiment. I'll highlight it real quick in this one.
Yep.
How do
Oh, I
we
did not know.
know that? What's
Okay.
that?
Wait. That's pretty cool what you just did.
Yeah,
How
yeah.
did
You
do
can.
that?
The student can annotate on your screen, and then they can erase it. And it's kind of nice for us to just reference.
So can I do the same?
Yeah, you can. So somewhere on your screen, you'll see a
Annotate.
green bar at the top. Yep.
Oh, okay, so if I choose, there's a pen or something like that? Still, I don't have a pen.
You might have to move your mouse up towards the top of the screen.
Yeah, so there's maybe you don't see that, but there is a black thing with a number of buttons, and one of them is annotate. I have an eraser, I have a stamp, but I don't have a pen.
Oh, click on the draw button, I think, and it will let you select a pen.
Wow. No, I don't. Okay, I will figure that out. That can be useful. I did not know we could do that.
Yeah.
I will try to figure it out. Thank you. Yeah. So I'm sorry for interrupting you. Can you ask a question?
Yeah, absolutely. So you're fine. So my main question is, we see the output here is the spin up particles, and then it goes through this, and we basically split the beam by the X component and then recombine the beam inside here. And then when we run it through another Stern-Gerlach, we see that the output is unchanged. So how does this, how do these facts lead us to conclude that there's some interference going on? That's what I don't quite understand.
Because you see that each particle, so let's say one particle arriving here, you see my pointer, right?
Yeah.
One particle arriving here is spin up, as you said. So it's the component, the Z component of its angular momentum is positive. That particle can be found if we were to measure with a Stern-Gerlach device like this one. It could be found with this experiment. It can be found with the X component of its angular momentum pointing to the left or pointing to the right. Right?
Okay, yeah.
That means that one particle has as many chances to go through here as to go through here. And then no matter where they go, we recombine them together. But classically, you would think that some went up here and some went down here. And you can think about this experiment with the particles going one by one. So it's not two particles interfering together, right? One particle that was selected with the angular moment, the Z component of its angular momentum positive, classically would either go here or here. Quantum mechanically, it's going to do both and interfere with itself in such a way that although the two possible positions were separated by the magnetic fields, you end up measuring the same Z component of the angular. And the reason for this is that although the two beams were separated, this does not amount to a measurement because you have not done anything to these beams. Now, if I were to add, and you can do it with your pen, you can, let's say, block, I don't know how to do it. You can block this, I don't know how to do it. You can block maybe the lower beam. As soon as you block the lower beam, then the outcome of the Z component here is going to result in as many particles found with a positive component as there are particles with a negative component of the angular momentum.
I think I see. Thank you.
So
That's much more clarifying.
if you think about, again, I'm sure you had a lab about that as well, the young slit experiment. You have light. Maybe I can stop sharing this. If you have a double slit, that's something you can do with a little laser pointer, right? And so you have two slits, and you shine light through these two slits, and behind you have a screen. And on the screen, what you're going to see are fringes, interference fringes. The distance between the fringes will depend on the distance between the two slits and the wavelength of the light and the distance of the screen. You have worked all these things out in optics. But as soon as you block one of the two slits, then you have just a diffuse distribution of light on the screen. Right? So as long as if you throw so much light that an appropriate description is by describing the light as a wave, then you say, okay, I understand that's the wave interfering, and like wave on like for example, if you were to produce wave at the surface of water, you could have a plank or something that you shake in the water. So you're going to create parallel waves. And if you create an obstacle with one hole, you're going to see those waves diffract through the hole. And if you make two holes, the diffractions of these waves, they will interfere, and you will see regions where the wave is big and regions where the wave is small, right? So if you think of light in terms of wave, that all makes sense. Now, if you do the experiment, and that's an experiment that has been done. I'm sorry. So I have to tell you that we are in my garage, and you are standing on the ladder, and I keep tripping on the ladder. So that's why sometimes you see me lose my balance. That's because I'm trying to get close to the computer, and I trip on the ladder on which you are sitting. Now you could do that experiment where you send photons through the slits one at a time. If the two slits are open, you're going to end up detecting photons only on these fringes, or predominantly on these fringes. Right? There is a cosine square modulation, right? If you block one of the slits, either this one or this one, you block one of them, then the fringes disappears and you see light everywhere. So that means that you cannot describe really the particle as you cannot describe the light as a wave anymore, because you are sending photons one at a time, but still there is this interference phenomenon that occurs, right? So that's the same situation as here, right? So you could think of this beam and this beam as being the light going through one slit or the other, but when you think about individual particles, one individual particle, you cannot say it goes through one or the other. Because if it were to go through one, then the next measurement of the Z component would be as likely to result in a positive value as in a negative value. Is that answering your question?
Yeah, I feel like I really understand quite well like why this is happening now. So thank you.
Okay. Okay, so now it's 4. I'm sorry, I've been long. I will try to spend less time next time. You want to spend some time, so let me close this tab. And would you like to look at problem set 1?
That'd be nice, yeah.
And so okay, the way, clearly it's going to be harder working online compared to if we were together in the classroom. But if we were in the classroom, the way I would do this, I would ask everyone to work on the problems, and then I would ask students to go to the blackboard to how they solve the problem or to show the difficulties that they have in solving the problem. So here it's difficult to do that. If you feel like solving the problem on a sheet of paper or on a tablet or anything, and if you feel like sharing with the class, that's great. Otherwise, what we can do as well is you work on it, work on the problem, and then you guide me, and I can write what you tell me to write on the blackboard. That's working. And so the first question is very similar to the first question in the homework. In the homework, you are asked to consider a solid sphere whose mass is uniformly distributed, and that sphere is charged on the surface. And you're asked to calculate the ratio between the magnetic moment and the angular momentum of that sphere. So here, that's the same question, except that we are asked to consider a disk uniformly distributed mass m, and with a charge q that is uniformly distributed over the edge of the disk. And you are asked to estimate, to calculate the ratio between the magnitudes of the magnetic moment mu and angular momentum L. So maybe I'm going to stop sharing my screen, and you have access to the question on your own browser. That's okay? I'm going to assume it's okay.
No, yeah, it's good. Sorry.
I know it's difficult. Okay, and at this point, I'm not doing anything. I'm waiting for your input. Oh. I need to set up a AC system in my garage because it's very, very hot here. Oh. I'm ready to take any suggestion of yours.
Okay, so I'll take a shot at it.
Great.
So you say to express the ratio of mu over L. And so just kind of referring back to your notes, it looks like mu vector is equal to Q over 2m times the angular momentum vector. So the mu vector over L vector would be Q over 2m.
So, okay, you have to, that calculation that we kind of went through together, that was looking at one particle. So let's say I have the z-axis. Oh, I should use the arrow. I have the z-axis. And I have one particle, I don't know if you see red. One particle of mass m and charge q that is going around in a circle, right? So in this case, you see that we have one particle with a localized mass and localized charge. So that's an example example, a system in which the distribution of mass and the distribution of charge is the same. Now you could have an object, let's say a ball or something, that is uniformly distributed in charge and uniformly distributed in mass. Then since this object can be broken down to a sum of points, and each point has this ratio between the magnetic moment and the angular momentum that we calculated together, the ratio for that object that has the same mass and charge distribution will be the same. Here, however, you're described, the situation that is described to you is one in which the mass distribution and the charge distribution are not the same. So that means that you really need to calculate the magnetic moment standalone, calculate the angular momentum standalone, and then do the ratio. Is that making sense?
Yeah, I think that makes sense.
Okay, so let's say that so maybe I can make the drawing, right? So we have a disk whose axis is Z, and the mass of the disk is distributed over the entire area of the disk. We can say that the radius of the disk is R, and the charge of the disk is just on the edge. And we can call that Q. Okay. So maybe we can start by calculating L. How would you calculate L? That's classical mechanics, right? So no problem there. And let's say, okay, let me add that maybe it's spinning with an angular frequency omega.
It's just M omega or MVR.
It's I omega, moment of inertia. The disk would be
I omega, where I is the moment of inertia. So then how do you calculate I?
Be the charge of the disk that is given to us divided by the period of the rotation.
So here you're talking about the
That's I
magnetic.
as in current. He wants I as in moment of inertia right now.
Oh, okay.
That's L, the angular momentum. So I here is the moment of inertia. So here, at this point, we are not talking about the magnetic moment. So how do you calculate the moment of inertia?
I just look it up in a table.
No, don't do that. No. Let's figure it out ourselves, right? We can do that. How would you do that? So if you have just 1 point, and if you had 1 point going around at the same frequency L omega, distance R with a mass m, the position vector is R. And let's say that at the time when the mass is in the plane of the blackboard, the momentum is pointing away from us. And L would be equal to R cross P, right? So that would be R cross M, the mass of the particle, times V, the speed at which the particle is going. But since I'm considering that R is in the blackboard and V is perpendicular to the blackboard pointing in the blackboard, I would have the magnitude of L. That is M, R, so that this R and this M. And then I have V that would be R omega. So I have R squared omega, right? So if I wanted to write this angular momentum under the form I omega, I would identify that I is equal to mr squared, right? Is there anyone who has a question about that?
No, that makes sense. I had forgotten, personally, I had forgotten how to derive the moment of inertia, but thanks for that reminder.
That's why I'm bringing that up. That's good. So we have I, that's mr squared, and that's for 1 point. Now here we don't have 1 point, we have a disk, right? But that disk, we can think of it as being made of a bunch of points, and just a matter of integrating over the area of the disk, mr squared, in which m is going to be the surface density of the disk multiplied by an element of area. Right, so I can erase this. Everybody's good with that? 1, 2, 3, it's done.
Yeah, go ahead.
Okay, so now the question comes down to calculating the moment of inertia of a disk. So how would you break up the disk to write an integral that provides the moment of inertia?
We can break it up into a bunch of rings and then just integrate from 0 to R.
Yes, that's what I'm going to do. So I'm gonna think up of small rings of radius r, and I'm going to integrate for that radius going from 0 to r, the radius of the disk. So dr, the little step in radius that I'm making. Now the mass of such a ring of width dr is going to be the width times the length of the ring, right? So the length of the ring is that's going to be 2 pi r. So 2 pi r dr is the area of a ring of radius r and dr. And then I can multiply this by the surface density, the surface mass density of the ring, of the disk, sorry. So the mass of the disk is m. And to get the surface mass density, I need to divide by the area of the disk, which is pi r, big R squared. Right. So at this point, I have, this is an area. And this is a surface mass density. Everybody's good? So this would be a mass, right? So here I would be just summing up the mass, that's the mass of the disk, right? Now what we have seen when thinking about 1 point is that the mass of the point has to be multiplied by the square of the distance of the point to the axis around which it is orbiting. So here, I just need to multiply by r squared. Right, and you see that this is a mass times r squared. That's a moment of inertia.
So you just add you just included the r squared on the numerator to make it the moment of inertia on there, right?
So here,
Yeah, it's a little bit blurry, so I wasn't able to see it very well, but I was just, it looked like at the very far right you added an r squared.
here, yes, the reason for this r squared is that we have seen before that the moment of inertia of a point mass around an axis is the mass of the point mass times the square of the distance to the axis. Right?
Okay, perfect. I was just trying to confirm that. Thank you.
So this is the area of the ring. So one of you, I don't know who that was, one of you suggested that we break the disk into rings. So the area of one ring, so an area that's measured in square meters, right? If I multiply that area by the surface mass density, so it's a mass per unit area, here I get a mass. And then that mass I multiply by the distance from the axis, which is just the radius, the square of the distance squared, which is just the square of the radius of the ring we're considering in the integration. Okay, so you see the pi simplifies. Let me rewrite that a bit cleaner. So I have I, and I have a 2 here, so I can bring that out. I have a m, which I can bring out. I have a 1 over capital R squared. And then I integrate from 0 to capital R. I have dr. I have r. And then I have r squared. And I think I wrote everything at that point. So that gives me r cubed, right? R times r squared is r cubed. Well, in order to integrate these, I'm going to get 2m over r squared. That's just a factor. And then the integral here is going to be r to the 4th power divided by 4. Taken between 0 and r. Okay. So that gives us 2 divided by 4 is 1/2 of the mass. And then I have r to the 4th power minus 0 to the 4th power, not just r to the 4th power. R to the 4th power divided by r squared is just r squared. So that means that the moment of the moment of inertia, the angular momentum is going to be the moment of inertia we just calculated, which is 1/2 of m r squared times omega. Is there anyone who has any doubts about what we just did? It's better to ask, right? If it's not clear, please ask.
Excuse me. Hello.
Everybody's good?
So I'm not sure it's only me, but I am having hard time to understanding the board. Like I cannot follow much because it's so blurry, and your voice is also cutting out, so it's not clear for me.
Yes, I understand it can be difficult, but I can.
So
There's not much I can do, right? Because if I bring the computer closer to the board, I'm going to lose area on the
no, so
blackboard.
it's showing that your network bandwidth is low. So that's why, yeah, most of the time the board is blurry and your voice is cutting out while you are talking. I cannot hear the whole sentence most of the time. So I'm not sure if it is happening for anyone else or only
It's the
me.
same for me. Yeah, I have the same problem. I'm missing all the math. Professor, if you use the whiteboard on the computer, maybe I cannot see the math and I also cannot hear. And
Yeah, it's so hard to read whatever you are writing.
it's just
because
impossible to follow. I don't know if anybody else is having this issue.
So I think we're all having the same issue. For me personally, I was able to kind of like deduce what you were writing by just kind of following along logically with the equations. So yeah, I mean, the board is kind of blurry, but listening to you say what you're writing down really helped out a lot for me.
But I'm also missing the, like I cannot hear the whole sentence. It's cutting in
Same
between the
here. I
sentence.
cannot hear either.
Okay, so what I'm going to do for next time, I'm going to try to figure out how to do this from my tablet instead. But I need to learn how to do it. At the moment, I don't know. I know how to do it on my computer, but I don't know how to do it on the tablet. I need to. I'm sure it's possible. And then in which case I would write on the tablet, and maybe that would be easier if I can share the screen of what I'm.
Right, that's probably better. Yeah.
Sure.
The reason why I have, so you see the notes that we went over. The reason why I decided to not try to use the tablet for handwriting is that I have a hard time writing small letters on the. So I always zoom in very much. So, but I will try. I will try. So next time I will try to use the tablet and we'll see if that's better. Okay.
Thank you so much. Yeah.
Yeah. Thank you.
I'm apologizing for the conditions, which maybe
No
are
worries.
difficult. But can we still try to clarify this calculation? I would like us to. At the same time, it's going to be 5. It's going to be 5 now. Can we make sure that everybody is clear with this calculation still? It will take 5 minutes.
Sure.
So here, I'm trying to calculate the moment of inertia of the disk. So one of you suggested that we break the disk into rings and that we sum up the contributions of the rings, right? So for that reason, I do an integral from 0 to the radius of the disk, big R. And first I write the element of area, so the area of the ring. So that's the circumference of the ring, 2 pi r, the small r that we're integrating, times dr, right? 2 pi r circumference, dr is the width, so the product of the two is the area. Now if I multiply the area by a surface mass density, I get a mass, so that will be the mass of the ring. So the surface mass density is the mass, m divided by pi r square, which is the area, big R square. That's the radius of the disk. Okay, so at that point I have integrated the mass. But if I were to calculate that integral, I would just find the total mass of the disk, which I know already, so that's not interesting. But if that mass element I multiply by r square, then the integrand is the moment of inertia contribution from the ring, right? So then this integral I'll rewrite down here. I pull out the constants. So I have the moment of inertia. That is, you see there is a 2 here that comes here. There is the mass of the disk that comes here. The square of the radius of the disk that comes here. And then I have the integral from 0 to the radius of the disk. That's that integral. And then the only thing that I have left is the dr and r times r squared. So that gives me r cubed. And the pi canceled out. And there is a 2 pi r. The pi that comes from the 2 pi r cancels from the pi r squared, that is the area of the disk, which the pi is gone. So I have 2m over r squared times the integral from 0 to capital R of dr r cubed. So you should know how to calculate that integral, and you find 1/2 m r squared. And then if I multiply that by omega, as you suggested, I get the angular momentum. Okay. So we are running out of time now. I'm sorry, I was a bit slow in the first part. Maybe on your own, calculate the magnitude of the magnetic moment. And what you can remember, what you can use for that is that the magnetic moment is equal to I, or maybe I should not call that I, maybe I'm call that I round, the electrical current times the area. And so if you have a current loop like that, with a current I that is flowing around, that current loop is encircling an area the product of the current with the area is the magnetic moment. Now in the case here, you see that you have the charge that goes around in a time 2 pi over omega. So that's the time it takes for the charge to travel all the way around the circle. So the charge divided by the time it takes, 2 pi over omega, is going to be the current. And if you multiply the current by the area of the disk, you're going to find a magnetic moment. And then it's just a matter of taking the ratio between the two, and you will have found the ratio between the magnetic moment of the disk that is charged on its edge and the moment of inertia of the uniformly the uniform mass distribution of the disk. Okay, everybody can do that.
Yeah, I think so.
Yep.
That
Yeah,
makes
I
sense.
think-
Yeah, it's
You do that
kind
on
of just
your
about
own. Sorry, someone was saying something.
yeah, I guess it's just more about kind of refreshing some of our
Yes,
concepts. So
yes.
yeah.
And also, I want to do that so that you are ready for the homework.
Professor, is there a way for you to post
Help you with the homework.
the solutions to these problem sets so I can double check my work?
Now, if you want to double check your work, we'll do it in class together. I'm not going to, you see that I do a lot of writing already. Unless there is a major problem, I would rather not. I mean, these problem sets, they are more for discussion between us. I think we should resolve the problem in class. Okay? Okay?
Okay.
Okay, sorry for going in time. I'm going to try to make it work with a tablet, and we'll try that next time. Okay?
Professor, what I personally believe is the problem is not with the board, but with the internet connection. The bandwidth is low. So the board is, I guess, fine, but the internet connection
but
is
you
the
realize that I cannot fix. I mean,
yeah.
that's something to address. The only thing we can do is communicate over internet. So I'm providing notes, I'm providing exercises and homeworks, but aside from spending time with you live via internet, that's the only thing. I cannot do anything else. Or at least I cannot think. If you think of something else, I'm happy to consider anything. But I cannot think of anything else.
Professor, I do have an idea. I'm not exactly sure if it would be possible for you to do this, but from previous experiences, I'm not sure if perhaps pre-recording the lecture and posting it, and then having the students watch the pre-recorded lecture and then using the class time specifically more for questions about the pre-recorded lecture and or homework. Is that something that would be possible for you to do?
So I can do that. So I did that last spring. Mm-hmm. Recording these things is highly time consuming. It's huge. I mean, like I was doing 1 hour, I was burning 3 to 4 hours for 1 hour.
I see, that makes sense.
So that's hard, right? And then I'm not sure about, because you see the big thing that we are losing is if we were together in class, I would see, you feel the moments where students in front of you have a hard time understanding what you're doing, and we lose that. So, I mean, in principle, you should all be able to read. And as I go, so today I went over the notes, kind of talking by myself, but I would encourage you to interrupt me at any point so that we have a live discussion instead of, well, you're going to go over let's say I record videos, you're going to watch the video and then we meet together and you're going to say, oh, I did not understand when, but I don't know. I think it's easier if we are able to communicate in real time and answering your questions really real-time communication as well. So I mean, I can go back to recording things. I'm just doubtful of the actual use of this, given that I am providing the notes for you to read and to think of, and maybe prepare questions for when we meet. I don't. I mean, tell me what you think, but I don't see what recording my voice when you're not able to interrupt me, what is that going to bring?
Okay. Yeah, no, I totally understand. And I appreciate the time and effort that you've put into making it possible for all of us to read your notes and just kind of have access to all the problem sets before time. Yeah, so I mean, yeah, it's definitely like a lot of effort, but it was just an idea that I had. I wasn't sure exactly how much it would take.
Note that I'm not rejecting the idea of recording anything, right? I just don't really understand the function of it, because if I'm talking by myself, I've done that in the past. I was just talking by, and that's the thing that is difficult, in fact, because I was finding myself in my garage talking alone. I don't know what my neighbors are thinking, but and then there is no there is no exchange in that time, right? Since you're not there, I'm by myself. So I don't understand what the recording brings. If you think the recording is important, I will do it.
Okay. No, I definitely. I think somebody else brought up the idea of doing it on a tablet. I am open to everything, and I'm sure if other people have other opinions, they would voice them as well. Like I think using the tablet would work as well too, and I'm open for all the ideas. So
yeah,
I'm gonna try, and maybe what I will. I'm gonna try. Tonight I can't, but tomorrow I will spend some time trying to understand how that works. And when I will feel that I know, what I will do, I will post a message on Canvas asking for some of you to show, whoever is available, to show up and experiment with me, just to make sure I know what I'm doing. Okay.
Yeah. Professor, is it possible that The problem is that you are in the garage and your network is not that great there. So if you change the location to somewhere,
I can see the display of my signal in the garage. It's completely saturated. That's not, and in fact, so it's true that I'm in the garage, but my house is very small, and I'm in fact 5 meters away from the Wi-Fi. Right, it's very close to me. So and I have full signal on the computer. So I don't believe that's the issue.
Okay, thank you.
One also small request would maybe be to like also just like record the Zoom lecture just in case we may want to go back. That could also help if someone wants to go back to the lecture afterward.
The meeting we just had, you would like to have that recorded?
Or future meetings.
Well, yeah. So
yeah.
I like that request because I think that would fix the audio issues that people are having. I think that if you were to record your own voice, we might be able to go back after and kind of catch some of the things that we missed due to the Wi-Fi issue.
Yeah, so we can do that. Just like today, I see that there are 29 of you in the class. I would not like that it evolves toward people not showing up because anyway the guy is going to be recording his voice alone in his garage, and I can listen later, right? So I think what is important is that we talk together, and I can try to answer your questions with the difficulties that you have. So, but next time we can try to record, and I will post the recording on Canvas. So one thing that comes up with that. From last, I don't know if it has changed this semester, but in the spring semester, the difficulty was that I had to remove the videos after a week or week and a half because like you see, we have been 2 hours together. That's quite a big video that results from that. And so there is only a limited amount of space that is available for sharing on Canvas. And so the videos will be available just for a short amount of time, so like of the order of 1 week. But yeah, I can try to do that next time. Okay. Any other question or suggestion? I see that there are messages.
There is one possibility for the audio. And I know it's possible to join Zoom through phones. So if you were to use your computer on mute in one screen and then join through another account on your phone for the audio, that might help slightly with the bandwidth, depending on how good your phone bandwidth is.
Do you know how to do that, Philippe?
I personally do not know how to do that, but I know it can be done because that is how Dr. Gondola would often join meetings through his phone.
Yes, I have seen that when you start a Zoom session, that's a question that you ask, but I never really understood, what it meant. But that's something we could look into. Yes. Okay. Okay. Shall we stop here? It's 5:13. I'm happy to spend extra time anyway, but it's 5:13 now, and we meet again on Wednesday. So look at the notes, and I will try to do the class from my tablet instead, and hopefully it will work better. Okay.
Thank you.
Okay.
All right.
Thank you, Professor.
See you all on Wednesday.
Thank you.
Thanks.
Thank you so
Bye-bye.
much.
Bye.